Hello and welcome to the Ali NOAA Climate Change Short Course. I'm David Herring, Director of Communications and Education within NOAA's Climate Program Office. And on behalf of NOAA and our partners in the Osher Lifelong Learning Institute, it's a pleasure to bring you this lineup of world-class climate science experts to give an overview on our modern understanding of Earth's climate system. In today's session, we're going to hear from Dr. Michael McCracken, who is a senior climate scientist for the climate change programs at the Climate Institute based in Washington, D.C. Dr. McCracken is going to give a presentation focused on geoengineering and the ethics and legal issues surrounding geoengineering as a possible solution to climate change. This session is going to feature an exploration of the pros and cons of geoengineering. This term, geoengineering, refers to deliberate manipulations of Earth's environment to either prevent an undesired effect or to bring about a desired outcome in the climate system. Some people have proposed various geoengineering solutions as a way to stave off climate change. But the questions are, at what cost? What might be the side effects? Are we willing to live with those side effects? Could these efforts actually work? So these important questions are going to be explored in detail by Dr. Michael McCracken in this session titled Ethics and Issues Surrounding Geoengineering to Mitigate Climate Change.
After sort of starting with a quick review of a lot of what you've covered, I'm going to get into this issue of climate engineering. I have a lot of material here. It'll be available on a PDF afterwards, but I hope by the end you'll have a sense of what the issue is here and the decision that has to be considered by the public, because scientists can come up with options, but it's really the public that decides what gets done. Now, this title was sort of proposed, I don't know, several months ago. I want to sort of say I'm going to cover a few more things, so I have a sort of longer title to give you a sense as a table of contents. I want to talk about the incentives. Why in the world would you think about going out and trying to change the climate? I want to talk about some of the options. I'll talk about some of the issues in ethics and some of the things relating to what we're doing. Now, mitigation is one way to get at it, and I'll talk about that, which is reducing emissions. Climate engineering is sort of trying to counterbalance the climate change that has been occurring. And in fact, let me start with some definitions. So you saw I switched from geoengineering to climate engineering. There are actually a number of ways in which we engineer the planet. For example, assuming this works here. Here we go. We do some things that are trying to benefit society. One of those is we've re-engineered the land surface so we can grow food for the planet. So that's a very positive thing, but it has certainly changed the environment in some ways. We've done things so that we can have water in various places. So we've done some things that affect the water cycle in various places. Now, we've also had some unintentional things that impact the environment. I see some of you taking notes. Let me again say, this will all be in a PDF file. You're going to wear out your hand if you try and take notes. We've done some things with air and water pollution. We're impacting global cycles. There's emerging concern about what we're doing to how much nitrogen we're doing to change the environment, which sort of causes lack of oxygen in various places and phosphorus. And we're also changing the climate. That we're not doing this intentionally by using fossil fuels, but it is a way in which we are changing the climate. So what climate engineering is about, which is I think the emerging term people will be using, is to try and go out, instead of inadvertently or unintentionally doing it, trying to intentionally change the climate and counterbalance what we're doing in some way, try and get it back to the normal that we have and that we're used to and that species evolved at. And if some of you can't see so there are two general approaches. One is to go after the cause of the problem, that is try and pull CO2 out of the atmosphere. We're putting it in by burning fossil fuels and coal and gasoline and things. Pull it back out of the atmosphere. That turns out, as you'll see, a little bit hard to do. And then the other is to say, well, if you're trapping heat in the atmosphere due to the CO2 that you have, let's have less heat from the sun coming in, and we'll try and counterbalance what's happening in the energy that's trapped. So those are sort of the two general categories of approaches. So you've had these lectures that have gone on. You've basically seen that we're in quite a dilemma. Fossil fuels provide a tremendous benefit to society. They supply something like 80% of the world's energy. They're relatively inexpensive. They're available night and day. There are a whole bunch of benefits to it, but they create a whole bunch of issues with respect to the environment. Some of the ones are relatively easy to deal with. Air pollution, we've worked hard and made cleaner burning devices and things. Some of them, like climate change and ocean acidification and things like that, are becoming very hard to deal with because of how much CO2 is being embedded to the environment. So I'm sure you've seen this curve, a sort of the CO2 increase at the Mauna Loa Observatory. You see it going up. The rate of increase is accelerating given where we are, so we're headed to warmer conditions. One thing I want to do here from this curve is just give you a sense of the magnitude of the problem. This is measured at the top of Mauna Loa, which is a mountain in Hawaii. We think it represents the clean air of the northern hemisphere and sort of what's happening. And these up and downs are the seasonal variation. So the level is highest in about March, and then you have growth all through the growing season until September or so, and then you start getting it returning. So the difference between these represents the net greening of the entire northern hemisphere over the annual cycle, and then sort of it's released. And the northern hemisphere is sort of separated meteorologically from the southern hemisphere. So if you multiply this mixing ratio, this amount of CO2, by the volume of the northern hemisphere, you find out the mass of carbon that we're putting into the atmosphere and everything, or that the biosphere is putting in and out of the atmosphere, and you can compare that to fossil fuel emissions. So if you multiply that volume, it turns out this is about 7 or 8 billion tons of carbon each year that the biosphere net greens when your gardens green up and the trees get leaves and everything, and then you lose it. Well, 7 or 8 billion tons is right about how much fossil fuels are being consumed each year and added to the atmosphere. So that's a big number. Okay. Now, why doesn't the amount go up each year by the amount we put in the atmosphere? Well, half of it mixes to the southern hemisphere, and about half is taken up by the existing trees and plants, take up some, and some gets mixed into the ocean. So the annual increase is about a quarter of what we're putting out. So, and that turns out to go over time. So if you multiply these numbers by 4 and call it billions of tons of carbon, you come out to almost what the emissions are doing. So here we go, and we're headed up, and we sort of pretty well understand that part of the cycle. This change in the atmospheric concentration of CO2 causes warming influences. So this is just sort of a record from the past, the pre-industrial period to the present, of the warming influence of CO2. There are some other gases, and I'm going to talk about some of these later, methane and nitrous oxide and the halocarbons, and some things that create ozone in the troposphere. So, pollutants, these aren't talked about much, but it turns out they're becoming recognized as important. And then there are some cooling influences. Because we put SO2 out when we burn coal, the SO2 becomes sulfate, they become small particles in the atmosphere. When they're taken into clouds, you get more small drops. It makes the clouds brighter, and that tends to reflect more radiation. So that's sort of an important thing to know, because there's some people who want to propose to amplify this cooling effect as a way of trying to offset the warming influence. So the sort of geoengineering or climate engineering approaches are trying to pull CO2 out of the atmosphere or make more cooling influences over here. Our net effect is sort of warming. Because the net is about the same as CO2, that is the sulfates and all these other things cancel, most of the world negotiators focus on CO2. And they just sort of think that's the only thing we have to deal with. And that's becoming recognized as a mistake. There's more we can do because of that. So carbon dioxide is the main greenhouse gas. Let's see, let's go. Talked about sulfate and the net. Okay, this is a record of what's happening because of that. The temperature's going up. These are decadal averages. This is sort of NOAA's way of doing it. The blue dots are annual values. The red is the decadal average. It's sort of been going along, bouncing around down here, and then it went up through this period in the middle of the 20th century. It went up. Some people say it was really warm during the 1940s. It's really strange in a scientific sense that all these warm years occurred during World War II. Somehow the world knew to be warmer during World War II. It makes the scientists say there must be something wrong with the measurements. And so there are concerns about whether this is really this high or whether people are identifying some biases that occurred, perhaps because the U.S. Navy ships and how they took measurements compared to earlier. So this may actually sort of ease off, but it goes up. People have been looking at what it's due to. The black line is observation, so it's going along and then it goes up. The blue is if you just take solar and volcanic effects, then you fit pretty well until you get to a post-war period when the CO2 concentration started going up. If you consider all the factors, the human factors and the natural factors, you actually get pretty good agreement with observations, except maybe during World War II, which may be those measurements. That was sort of identified in 1995. In the more recent assessments, they've actually done it regionally, and you can see the blue is just the natural influences. The red is what happens, pink is what happens when you include all of the influences. You get pretty good agreement on all of the continents. You do pretty well on the land area. You don't do very well on the ocean, and it's during World War II. I mean, so it's kind of interesting what's going on. So we think we have a pretty good handle on what's causing what. That's led the Intergovernmental Panel on Climate Change to say things a few different ways. This first one in 1995 it said, well, the evidence, if you balance it, suggests a discernible human influence. So it was sort of suggestive. 5 years later, 6 years later, they're saying new and stronger evidence that most of the warming over the last 50 years is due to human activities. And in the 2007 assessment, they're saying warming of the climate's unequivocal. Most of the observed increase is very likely, which means 90% chance or better, due to human influences. This is important. These are scientific statements that have to be broadly agreed to. They represent a full international consensus. The IPCC is often painted as a green organization. When you get 180 or 90 countries to unanimously agree on something, let me tell you, it's not cutting edge. I mean, they've smoothed everything off. So these are actually pretty cautious scientific statements and sort of agreed to by the policymakers. And when our groups say it's this strongly, that's a very strong scientific statement. It's certainly strong when you have every nation in the world agreeing with it, and basically every national academy and others. Okay, so what about the future? Well, here go the emissions up, up, up. We've had a little dip for this period of the sort of recession we've had, but it's projected to go up at a pretty high rate. This is sort of the graph that Al Gore had in his movie, that you go back several 100,000 years from the ice cores, getting estimates of what the CO2 concentration is. You can do in the bubbles, and then you go up to we're here already, and you can go way high up and have much higher concentrations. There's plenty of coal around. If you've seen the new ExxonMobil ad, they say, oh, there's all this stuff in the tar sands. We can have it for 100, 150 years. We can go way high up on concentrations if we don't get off the fossil fuel cycle. So IPCC has then done some calculations of what that's going to mean. This is sort of the black is the observed, and then what happens if you continue on with a high emission scenario is the red, green is the middle one, and purple is sort of a low one. That's sort of getting over to green energy pretty quickly. These are all pretty significant increases, and these are all above the 2000 temperature, not above pre-industrial, which is what people talk about. So you have to add, sorry, it's in red here, another sort of 0.6 of a degree. So you're talking about 2.5 to 4 degrees Celsius. So you multiply by almost 2 to get the Fahrenheit change for the world average. And most of the change occurs in high and mid latitudes, higher than average over the continents. Now they did this other curve too. They said, what if we could stop right now and keep the concentrations of everything constant and didn't do any more? That's kind of a hard thing to do. To do that for CO2, you have to cut emissions by 85 or 90%. So, but we're going to do it. And then they also had keeping sulfate and some other things the same. And so this is really sort of a geoengineering experiment. It's sort of saying, because the SO2 particles only stay in the atmosphere a couple of weeks, and so if I want to keep that cooling influence, I have to put something in to replace that. So I'd have to put SO2 in the atmosphere to replace it and keep the cooling influence, where I have to go almost to zero emissions for CO2. So this is actually a sort of sign of a geoengineering case. It has some continued warming because the ocean is creating a lag, and it takes a little bit more warming to get up to up to the equilibrium value. So I'm going to use this as a sort of reference graph. This actually goes out 2 centuries instead of 1. The purple here is sort of the observed. This is sort of what's projected if you go out and you don't do any controls. It goes way to the high level. And so what do we have to do in order to try and keep us under control? Because of those projections of temperature going way up, you get all these projections of impacts, and I assume you've heard about some, although it might be a course for next year to look at these kinds of impacts. Because fossil fuels are such a benefit, you look for the ones that would have big impacts. I mean, you're not going to stop using fossil fuels because of some little impact. So if there's a big one that affects health, more severe weather, infectious diseases, other kinds of things, agriculture gets a little bit of benefit because CO2 in some places can help things grow better and use water better, but there's also some problems with pests and weeds and temperature change and soil moisture. Forests change. They're sort of very used to particular kinds of climate in particular regions. You sort of see that when you go up a mountain. And so they'll shift to be different, but it takes time to shift. Normally what happens is your existing forest is stressed and dies and burns, and then a new kind of species grows up. There are water use impacts because you shift storm tracks, and you're hearing about some of those in the southwestern U.S. There's impacts on coastlines because of rising sea level, because glaciers and ice sheets are melting and things. There's ecosystem impacts. It affects the wild species and the biodiversity and migrating species. And then there are a number of societal impacts. We did this Arctic assessment, which was very interesting, and those people located their communities and have for thousands of years right on the barrier islands. They did that because they wanted to get food resources from the ocean and from the land. And so where do you locate? You locate right on the barrier island. Well, these are frozen barrier islands. Okay, so they're pretty fragile things. When the sea ice melts back and retreats, the winter storms come up, churn up the waves, it comes in and it sort of destroys those barrier islands. The Government Accountability Office did a study a few years ago about what's going to happen with some of these villages. There's about 150 or 160 of them. They're going to have to relocate. Now you say, okay, well, they're just going to relocate. The estimated cost for doing that is about $500,000 to $1 million per person, because you have to move the whole community, all the infrastructure, build it up to standards. It's a huge cost, not just where do you build, but what do you have to do. So there's all kinds of interesting things. So IPCC has done sort of this burning embers diagram, that is, as you increase the temperature from sort of where we've been, and we're about here, and start getting some impacts. If you head up to 1 or 2 or 3 or 4 or 5, the impacts get more and more severe, and some of us say they may be underestimating some of these. But the international leaders have sort of agreed we want to avoid this dangerous anthropogenic interference, so we don't want to go above 2 degrees C. So there will already be some impacts, loss of a lot of mountain glaciers and other kinds of things, but we'll avoid some others. So what we're going to do is try and can we keep the climate from warming below those levels? What are the challenges of doing that? Okay, so if you take this diagram, I put a sort of safe possible non-temperature zone at 1.5 instead of 2, but you want to be somewhere in this range. I have to get this down to here. Okay, so what is my potential for doing that? And that's going to be the question. But in starting, I want to sort of quote the daughter of a friend of mine. She went home one day very discouraged, having looked at this previous graph. Not that one, the one before, I guess, at this, and talking about it. And, oh, my heavens, becoming very pessimistic about doing that. And what her daughter said to her is, geez, you can't take away my hope. There must be a solution to this. Can't we do something about it? And that's what we're going to try and see. What can be done? Is there a path through this if we work at it? The answer, I think, is yes, but that's really the question to work at. So where might we try and interfere and get into the system and make some difference? So this is sort of the interconnection of a lot of different things. I mean, people want to have improved well-being, so they want more goods and services. That takes more energy and products, leads to more emissions, leads to higher concentrations in the atmosphere, leads to climate impacts, leads to them affecting ecosystems, and then they want better well-being. And so you're sort of going round and round. And the question is, where can you interfere with this? Where can you do things? Well, on the one hand, you can sort of ask for less kind of thing. So conservation is sort of getting by with less. That's one step. Another is efficiency, trying to do and produce your products with much greater efficiency. The next is to try and say, well, with what I do, I'm not going to produce those emissions that change the atmosphere. I'm not going to do that. And so a lot of what is called mitigation fits here. This is the emission and capturing emissions that are coming out of power plants and things. So now I have the emissions in the atmosphere. Then comes sort of the first of the climate engineering approaches. Namely, I'm going to try and say, well, okay, if I put it in, I can pull it out. So can I pull it out of the atmosphere? And I'll be talking a bit about that. But now if you let the higher concentrations go in the atmosphere and they're going to cause climate change, can I upset that? And that's where solar radiation management comes. I would try and allow less heat to go here, to go through and affect the impacts. Now I can try and adapt to have less, have the climate change have less effects on me. I can build higher levees along the seashore and other things. So there's adaptation, and I'm not going to talk much about that. That is something you could cover next year. And then there's suffering. I mean, what you can't do on here is going to end up with suffering. And suffering isn't just people suffering. It's you're going to have to relocate. There are going to be people along coastal environments that have to relocate, or that aren't going to have the resources, not be able to do what they do now. And if you look at what happened in the past when climates have changed, areas have been abandoned. That's what happened with a number of indigenous tribes and others. They just left the region and went somewhere else. That's harder to do today with so many people. So we'll be sort of looking at this path and what we can do about these things. So the first one I'm going to talk about is a little bit about reducing demands and emissions, because you sort of have to have a sense of that. There are a couple of things we can do in here. I won't talk specifically in details, but I just want to give you a conceptual sense of that, because if we don't do this, we can't do anything else. This has to be the first thing it's just an absolute must to do that. So their conservation is sort of reducing the demand for energy and for products. Efficiency is doing it better. Mitigation is switching to lower, no carbon sources of energy, renewables, and other kinds of technology improvements. Now, the first thing, an aspect of that is, and it's talked about most in the negotiation, is reducing the CO2 emissions. CO2 emissions are important to reduce because a fraction of them will stay for thousands and thousands of years. I mean, fuels were developed over very long times when they were buried in the plants were buried and then became fossil fuels. And so this takes a long, it's important to get after CO2. But there are a number of other, I guess, and you'll see that in these plots of what people do. And these are frequent plots that appear sort of in the literature about with CO2, which is, this is CO2 concentration going up. And what is pretty evident from doing some of these things is it takes decades to get that started. And you can see there's a long lifetime. Even if you have 100% reduction in emissions, there's a lot remaining over a long time. And so the warming that occurs, even if you start today and start doing things, you don't get much effect on the warming for quite a long period of time, for several decades. And that's because of the inertia in the system and the long lifetime of CO2. And that's led people to, that's led, as it sort of comments here, to people to say delay. Why should Congress act now if there's not going to be any effect on the climate until 2050? Okay, so I don't have to act now. I'm just going to let it keep getting worse and worse. And so it's a reason for delay. And so in that sense, the ethical issue is you're sort of passing this on to future generations, your grandchildren and stuff. And if you listen to Jim Hansen talking about it, he talks about in his written books about what's the impacts on his granddaughter and future generations. And that's a very important issue. But it turns out there are some other kinds of species besides CO2. There are short-lived species, things that create warming that only last in the atmosphere for a very short time. The most obvious of them is black carbon. When you put out black carbon as soot, that absorbs solar radiation, and so it makes the atmosphere warmer. If you do it, especially if you do it over bright surfaces, and there's Secretary Clinton is in Greenland right now, and one of the initiatives they're talking about is reducing the amount of soot that goes in the Arctic, because you get soot going over white snow. Normally the solar radiation be reflected out to space. With black carbon, it's absorbed and that heat is there. And then the soot deposits on the snow, makes the snow darker, and you reflect less. So it's really important to get after these short-lived species. And in fact, if you look at the warming influence caused by emissions during the 21st century, which are the ones that we might be able to reduce, in terms of policy, these are sort of the components of it. So the blue is sort of the carryover from the 20th century. This is mostly CO2 that has a long tail. There's going to be a lot of it around for a while, and you can't get below that. This red is the warming influence from CO2 emitted during the 21st century. And so this grows over time, and it has a very long tail to future generations, which we want to get out. But these pollutant emissions, methane, which is sort of just natural gas, and the pollutants that come out that create ozone, they have a lot of warming influence too. And so if I could get these, and these only have lifetimes of months to a decade or so, if you can get their emissions down, then your warming curve isn't going up like this, it's only going up like that. And that will greatly slow the warming and allow for a greater transition away from CO2. And it's even more important if you think about the contribution of black carbon, which is pretty uncertain. So if we can get the black carbon out from use of kerosene, from use of small cooking stoves, you may have heard there's a small cook stove initiative the United Nations is pushing to help people around the world and stuff. So if you can get the black and the orange and the green out of here, you've done a lot to help get things started. So that's been what's been a very new focus. There was in the past month or so a report that just came out trying to really first put this on the international stage from the United Nations Environment Program and World Meteorological Organization. It's nice they did it. This is something I've been sort of pushing on for some of them for a couple of years. But this is a graph. It's a little bit complicated, but let me just show you sort of what it means. It goes from 1900 to sort of 2100 or almost 2100. This is the observed warming, and so then they're looking into the future. If you just let it go, that sort of no controls, then that goes up here. That's this reference curve, and it takes us up to about 3 degrees warming by the end of the century. If you just go after CO2, which is sort of what the international negotiators are talking about, you only start to tip this curve after quite a while. So you don't get any early impact, and so that's a reason to sort of say, well, I'm just going to delay. If, however, you can go after the CO2 and methane emissions starting quickly, and they have a number of approaches to doing that, you can start limiting that warming immediately and reduce this curve, bend it over, and try and stay out of this dangerous level, which is somewhere in here. So you can make the curve go over there. So it's important to do. If you only do this, of course, this will keep going up. It'll just create an offset. So you have to do CO2 as well to really bend it over. So we really have to do all of those kinds of things. The sort of comments about what you have to do to get after the long-term species. I mean, for the CO2, we've got to get fossil fuel emissions of CO2 down by 80 or 90% to stop changing atmospheric composition. Developed nations need to demonstrate that that can be done, that a modern economy can prosper on low CO2 emissions, and we haven't done that. And so it's a little hard to preach to the developing countries when we haven't shown that. They have to work on, or we all have to work on reducing deforestation, and we may have to try and figure out how to scrub CO2 out of the atmosphere because also of ocean acidification. The short-lived species, we can really go after. Nobody wants methane to go out. I mean, you'd like to capture it. You don't want natural gas leaking. People want to collect it. And so a place you might collect it from, for example, the Chinese are ordering machines from Deere to suck the methane out of coal mines, because if you leave the methane in the coal mine, it explodes. Then they have miners killed, and then they get social disruption. They don't want it. There are a lot of reasons to go after these other pollutants. So you go after methane, you go after air pollution, you go after black carbon, and there are a whole bunch of other reasons to do that. In fact, many of these other countries are already doing that, and it turns out it's going to make a big difference. And we have to do it more too, but there are many things to do. So those are sort of the first two steps. And if you do that aggressively, you can take this curve where the temperature was going way up here down to maybe somewhere in here. So we're not at 2 degrees and less, but we're at 3 degrees, but we've got a much more manageable program, effort or thing to control. So if we stabilize this at sort of this 550 parts per million, and remember we're at 390 now for CO2, we might get to there. Okay, so, but that's not getting us down to this safe region. So what else can we do? Do we just have to suffer this warming, or can we do more? So that's where we come to carbon dioxide removal as the next kind of thing to take on. So what is the potential for that? And so I've sort of added that because it's an extension of mitigation. It's reducing the amount of CO2 in the atmosphere. And there are two general approaches to it. One is to try and enhance the natural sinks, make forests and other things, the oceans take out more CO2 themselves. And the other is to try and scrub it out of the atmosphere. The trouble with most of these things is it takes a lot of time. This is a lot of carbon to pull out if you have to pull out the equivalent of the greening of the northern hemisphere or something like that. So what are ways to do it naturally? Well, one is reforestation. And so there's been a lot of forest regrowth in the northern New England and across parts of the United States. You can put forests in new areas. But that does compete for land, and it competes for nutrients, but that's one interesting approach. There are efforts to try and gather biomass and just bury it in various ways. Sometimes you might make charcoal, and if you put that in the ground, that's nice because it helps hold moisture. And so if farmers were to do it, it helps be a fertilizer for their soil, or helps amendment to their soil and stuff. So there are ideas for doing it that way. There are ways of using biofuels with coal-fired power plants where you capture the CO2 and you try and bury it. It turns out not yet to be cost-effective, but it's sort of a longer-term approach. There's thoughts about increasing the uptake in the oceans. It turns out there are places in the oceans where there seem to be nutrients that aren't used, and that appears to be because there aren't some micronutrients, mainly iron, that haven't gotten there. Their land, and their ocean areas, they're far from the continents, and so they don't get dust that comes down and helps provide that mineral fertilization. And so there have been some studies seeing if you could do this. That will have some impacts on the oceans and the ecosystems in the ocean areas. And then there's this issue of scrubbing CO2 out of the atmosphere and then sequestering it, putting it somewhere, down in old oil wells or down in salt beds and other things. Nice idea, but the problem is if it's hard to take it out of power plants where the CO2 concentration is 10 or 20%, then it's really hard to take it out of the atmosphere where the concentration is 0.04%. So you have to have a huge enterprise to do this. There are a whole bunch of people trying to figure out, are there any shortcuts around that? And can you power that with renewable energy like in the center of Australia or something? But this is going to be hard to do. If I want to keep CO2 below 450, it's going to be hard to do this. But I should make the try. And to give you a sense of how big a challenge it is, this is just different units, let me say. This is sort of what we're talking about, and then this is billions of tons of carbon, which is the unit scientists use. We keep track of the carbon atom. The international negotiators want to keep track of CO2, and so they use a number that's 4,000 times larger about. That makes them sound like they're doing bigger things, but it's just their way of making it seem like a big number. Scientists sort of use the carbon one. So emissions are maybe 8 or 9 billion tons of carbon, so a little over a ton of carbon per person per year in the world. Deforestation adds a little bit more. So you say, so that's 10 per year coming out or so. The above ground biomass, all the vegetation in the entire world above ground, is about 600. So if I put out 10 billion tons for a year for a century, that's 1,000 or something. I'm clearly not going to be able to redo the whole global biosphere and duplicate it. So I can't just do it by reforestation. I can do some. If I can get some of the soils, there's potential there. So I may be able to get more into the ocean. The maximum people estimate is maybe 1 billion tons per year. I may be able to get 1 billion tons per year into forests. Maybe I can do some scrubbing and some biofuels. But this will only be significant if this number comes down instead of goes up. And so it was a little strange during the last administration when they weren't doing anything. They were letting this number go up and weren't controlling anything, and they were putting most of their research dollars into trying to do some of this stuff. because it really doesn't make a difference until you get that number down. But let's assume that they can do that. Let's assume we can get the maximum of 4 billion tons a year by all of these means together. If we go next to this chart, what happens? Well, that pulls the warming down a little bit if I build up to do that. And so I do go above this 1.5 or 2, but not by so much. So that's really something I want to try and make sure I can try and do. I really have to do this, but I want to also keep this in mind. But I'm still above this what's called dangerous level, where I may trigger melting of Greenland or melting of the permafrost and methane coming out and much greater change. So what do I do? Well, that's where you get to this issue of, there we go, oops, back one, sorry, of solar radiation management. That's sort of the next step to try and see what I can do. Can I counter that warming? And so if I want to stay in this range here, this is about how much I have to do. I don't have to do all of this, although there's an awful lot of discussion out there about assuming, oh, we're going to look at doing all of this or something. But I'll just keep burning CO2 and then I'll do all of this. The trouble with that is then I stretch it out for many centuries and the obligation for doing this. So can I do solar radiation management? Well, it's a very simple principle. It's basically trying to imitate a volcano. If I put something up, some ash in the stratosphere in this case, what happens, here's Pinatubo eruption, and this is sort of the opacity of the atmosphere, basically the inability of the atmosphere to have radiation go through. So it stops radiation coming through. So solar radiation doesn't come to the lower atmosphere, so it doesn't warm, and if you look at the temperature drops. So if I can imitate a volcano, a big one, I can cause the temperature to drop. Mount Pinatubo, a very big eruption, one of the largest during the century, sort of had the temperature go down 0.5 degree. That would be nice. That was about the difference I had before, so I need something the equivalent of a Pinatubo every year or two. Now, it's a little strange that this will work. This is a graph that goes from January to December in each case, and this is the warming influence of the CO2. And what to know about it is, gee, it's about the same everywhere around the Earth. So the warming influence by the greenhouse gas is about the same everywhere. But if I cut solar radiation, and I do it evenly everywhere, this is what it would look like. I mean, I get zero effect in the middle of the winter in the polar regions because there's no sunlight. I get, about double the value in much of the area to what's over here. So would the climate look the same of taking away this, taking CO2 out of the atmosphere and reducing solar? And at first glance, you'd say, no. Those would give different results. So all I'm going from is one climate perturbed by CO2 to a different climate that's now perturbed by two things. Well, what's interesting is if you take the models and you say this is the warming that you get from 2 times CO2, which is some warming in lower latitudes and a lot of warming over the continents and in high latitudes, and you take the radiation down about 1.8%, you get to this sort of even change we had, which is near zero temperature change over the whole planet, even though you had that very different seasonal pattern. So that's kind of intriguing. It's not something we understand exactly very well, but it does seem to work that way. And it turns out it also works for precipitation, which even surprises us even more. So this is the effect, it's a little dark, but the effect on precipitation, with the dark red being where there's been a significant change in precipitation. It's mostly an increase in the high latitudes, and then there's some shifts in precipitation belts in various places, and that can have important effects. The precipitation belt sort of shifts off Australia, and so that's kind of a problem for them and stuff. But if you go to 2 times, if you take this reduction, my heavens, most of these dark red areas have disappeared. And so some of these are probably just sort of random noise in the calculation, so most of it's disappeared. So, gee whiz, if I could do that and imitate a volcano, that would be interesting. And this is sort of a summary. If I look by latitude band, so this is from the low latitudes to the high latitudes of the northern hemisphere, the equatorial latitudes and the low latitudes, and this is for December, January, February with 2 times CO2, and June, July, August, so different months. You're seeing, more effect in the northern hemisphere in winter and stuff. These go down to very small effects. I mean, there's much smaller effects. It's near zero. It's sort of down in the noise of what's happening. So it's working on a latitude basis and a seasonal basis, and that's kind of surprising. All right, so we've got both carbon dioxide removal and solar radiation management as potential tools to use. How do they compare? And so this is sort of a chart to try and mention some of the issues and to understand that there are different influences. So the different kinds of climate engineering we have are different. Removing CO2 gets at the cause of the problem. This basically says, well, the way I'm going to get rid of one problem is to cover it up with another way of doing something. So there are a lot of people who are worried about, well, you're interfering with the system in some way, and you shouldn't really do that. We want to sort of keep Earth as it is without interfering, but so this is sort of two wrongs make a right, if you will. This response takes a lot of time because it's hard to move all that CO2. This happens quickly. If you could put up SO2 quickly, you could get cooling pretty quickly. So this is sort of seen for an emergency potential. This requires a lot of money. It turns out this is pretty cheap, especially if you put it in the stratosphere. Right now we buy chance sort of issue. The world puts up 20 million tons of SO2 into the atmosphere each year, or 30 or something like that. I only need a couple up in the stratosphere. So all I have to do is figure out how to get 10% of what we put out as sort of a small pollutant up into the stratosphere. Turns out that's not too hard to do. We don't think. This won't have much effect until I get emissions down, and this can have an effect sort of almost instantly if I want to. There's not many side effects to this because I'm getting at the cause of the problem, where there are going to be some potentially significant side effects here. If I basically remember the volcanoes, what people listen about volcanoes, they say pretty sunsets, pretty sunrises. Yeah, we'll get those, but it sort of whitens the sky. It makes it less clear. It'll cause some shifts in storm tracks because of where things are happening. It may affect the ozone hole and stuff like that. Removing CO2 is something you can do locally, so one country can just sort of do it. And that everyone doing it their own way will help. Some might grow more forests, some might do something else. If I'm going to change the whole global climate by putting SO2 in the stratosphere, I have to figure out how to get global agreement. That's going to be a lot of work and stuff. This final one is this issue of, well, what happens if something goes wrong and it isn't working? I can just stop this one if I pull out too much or whatever. This one, I have to sustain it for a long time. And if I'm sustaining this effect and I keep emitting CO2, then taking this away, I'm going to get a jump in warming pretty quickly because of that, if I take away the cooling influence. So there's a lot of worry about what happens if somebody starts it and then suddenly it stops. All right, so let's talk a little about more of the solar radiation management so you have a sense of that. I can try and do it at various levels. I can do it up in space. Have less solar radiation reach the Earth. I can do it in the stratosphere where volcanoes do. I can do it in the troposphere, which is where the SO2 from power plants has its effect. Or I can try and make the surface brighter and more reflective. That's a little hard because I have to go all the way down through the clouds to get to that effect, but I can try that. So I'll just sort of highlight what this is and give you a sense of the challenges. All right, if I want to stop it one way, and it would probably have the least influence, is it turns out there's a point called the first Lagrange point, which is a point where the gravity is the same, pole is the same with the sun and the Earth, and I put a satellite up there, and it'll go orbiting around just in there, and it'd be like a sort of solar deflector, and the sun would just be 99% as bright as it is, and everything. The only trouble is this thing has to be about 1,000 miles in diameter, and it'd be a screen, and you'd have to build a production plant on the moon is probably the easiest way to do it, or something. So it's a little bit expensive and far-fetched, but it wouldn't have many side effects. So, theoretically, there are people who have a few other ideas. The National Academy looked at something in 1992, which is let's have near-Earth orbits. I mean, you've seen the satellites; they're reflecting some radiation from the Earth. It turns out I need 55,000 of them or something, and each of them would have to be sort of 6 miles by 6 miles as a layer. It's huge. It would be crazy. I mean, how do I keep them from crashing? How do I keep them up there? And the sun would flicker. You'd have all these eclipses. So that isn't sort of proposed. Whoops. So the next one is to say, okay, let's try and really imitate a volcano. We have some experience knowing what they are. Can I get it up there? There are a range of ideas about how to do it, none of which have been really tested. But there's no research program on it. But it turns out the amount of material isn't much. If you could hold a couple of fire hoses up with helium balloons up at high levels and pump SO2 through it, you could get enough stuff up there. It's not all that much material. But of course, as storms come along and blow things around, might be a little hard. The National Academy actually found the cheapest way was just to take big artillery guns, put them on islands in tropical areas, and shoot 1,000-pound shells of sulfur up into the stratosphere. And they thought that would actually be pretty expensive. You hear people talk about the cost of carbon and reducing CO2 from mitigation, and people are talking $50 or $100 per ton or something. Their estimate was $5 per ton or something like that. So relatively inexpensive if you were to do it or something. There are a lot of people looking at high-altitude aircraft, especially if you specially designed ones. What you could do, you'd have to keep doing it and doing it. And there are a whole bunch of other ideas. Can you create a little volcano? Can you set off little balloons that float up there? There's a whole bunch of ideas that haven't really been sketched through, although the most looked at ones are probably some special kinds of aircraft and then this pumping it up in some way. And just to give you an indication of what some of this might do, if we're going along with the present sort of temperature going on, if you were to be able to put enough SO2 in the stratosphere, and one of these was for the Arctic, and the blue is for the Arctic, if you do it in the Arctic, and the other was for tropical, you can get the temperature back down. Now, nobody really wants to go back to the temperatures of 1880. We've sort of, in the 19th century, we've sort of gotten used to warmer conditions, but you could scale and you could try and limit future warming, but this becomes something you'd have to do indefinitely, and it would have to grow over time. Now, there's things you can do in the lower atmosphere. We could put out more SO2 if we were to do it wisely, and we wouldn't put it out where we do now for coal-fired power plants. You'd try and do it out over the open ocean and have a low concentration out over the open ocean where it wouldn't affect people, because this whitening of the skies not only affects the skies, it reduces a lot of the solar radiation that comes down for solar energy. When I was out at Livermore, we had the team from Sandia National Labs come over, and they'd built the first solar power tower in Barstow, California, which are those big arrays of mirrors that reflect all the heat to a particular point, and you make metal melt, and that's your circuit for making energy and stuff. And they had turned it on. They designed it. This was going to really show DOE how good it was. They designed it 110%, so it was going to really work. And it came in at 80%. And they came over to say, well, we know there's a volcano that went off, but how could that be doing it? We have this solar monitor here that's measuring solar radiation. It said solar radiation only went down by 2%. So how can that have an effect, a 25% effect on the device? Well, it turns out they were measuring the total amount of solar radiation coming down instead of just what's coming in the direct beam, which is what they need in the mirror. And so we said, go get the slightly more expensive instrument, and if you do that, and they did that, and they found that, the direct beam had gone down about 25%. So this is a real impact on solar technologies if you do this. Now, in the troposphere, you might be able to do it. The sulfur dioxide we see is this whitish haze you see when you fly over to Europe and stuff, downwind of industrial areas. Now it's much more downwind of China and stuff. So you could do this, maybe out over the oceans. There's another plan that says, well, I'm going to make, instead of just trying to make the sky brighter, I'll try and make the clouds brighter. And they have they try and make more small particles, and I'll show something on the next slide on that. You can try and increase the reflectivity of the land surface. You can try and paint your roofs white and roads white. That turns out to be a very small percentage of the area. There are ideas to try and make vegetation brighter, but by genetic engineering, everybody's a little worried about that one. And you can try and figure out how to make the ocean brighter. One way you say, oh, well, I'll float something on the ocean. The trouble is, to have so much big effect, it has to sort of be the size of a continent almost. It's sort of big out in the Pacific, But there's a new one that's actually interesting, which is blow bubbles. It's basically trying to imitate a ship wake and put very small bubbles that last over time and try and see if that'll help brighten the ocean. But the people one of the ones that's farthest along about cloud brightening proposes this kind of device. This is a ship about the size of a clipper ship, and it's a sailing ship. Okay, you don't see any sails, but this is a sailing ship. It's a trimaran, so it's very stable. And so what it's doing is spraying a mist of seawater out the top. So how does it get its energy? Okay, these are columns like a mast, and you spin them. And if you spin them and the air is blowing by, it will blow faster on one side than on the other. So it's just like an airplane wing, where the air goes faster over the top and slower under the bottom, and that creates a low pressure on top and gives the airplane lift. And these are the same way. You spin these, and that, because of the pressure you create, it basically caused the ship to go through the water. And you say, that's got to be crazy. Can that be big enough? Well, it turns out the Germans built a ship like this in the 1930s. And there have been some experiments. You may have seen a Discovery show. They went out and they couldn't believe it either, but they built one, and a small one, and it sort of worked. And so the idea is you sort of need the order of dozens of these per year to offset our CO2 emissions. Because they're trimarans, they're very stable. You don't have to set sails. You wouldn't need any people on them. You could actually remotely pilot them around, and they would go under the marine stratus clouds, those bright clouds off the coast of California. We sort of know this will work because if you look from a satellite down on these clouds, you see things like contrails in the clouds, and those are actually from freighters going underneath and the exhaust from their diesel engines coming off, going in the clouds. And with more particles for the water to condense on, you get more small particles, and that makes the clouds brighter. And it isn't by all that much, but if you do it in enough areas, you can make it happen. So it's kind of an interesting, far-out kind of thing. And, of course, it'd be easy to stop. And the amazing thing is, we've done some calculations trying to figure out these things. If you wanted to offset the CO2 concentration, you have to have a lot of these ships and stuff, 1,000 or something like that. But the amount of water that you're blowing up is only about the same amount of water as comes up in the Bellagio fountains in Las Vegas. Okay, it's just that it has to come up as a really fine mist. Okay, and we're all wondering, so what's the environmental impact statement going to be of blowing seawater up in the air? Okay, I mean, what? It's not a pollutant. You're just putting it out there, but you're claiming it's going to change the global climate. Okay, so we're all sort of wondering what will happen with that one. So if you look at these sort of collectively, these different approaches from space on down, with blue being sort of the good and red the bad, in space it's easy to make it bigger theoretically. It's just that deployment is really hard and expensive. Stratospheric aerosols, the hard issue is getting governmental agreement. Cloud albedo, well, it's got, you have to do quite a bunch of things all over the world with say, those ships or something like that. Doing things on land, you just can't make it big enough because you need the land for other purposes. So that's sort of where we are. Nothing's perfect, but we're working at it. Now, I've been talking about trying to change the global climate. Instead, one might want to try and talk about just going after some regional things, and this will be sort of the last thing I go through really quickly. Why go after the global one? Can't you just go after some regional worse things for a little bit? Like, could you limit Arctic warming? Could you use these techniques to limit Arctic warming, to moderate the intensification of tropical cyclones and hurricanes that's projected, to shift storm tracks so that the water comes where you want it to come a little bit? We sort of know that sea surface temperatures can do that. To try and sustain the sulfate aerosol offset, or to limit rate of ice streams going. So it'll be interesting to look at these kinds of things. For the Arctic, where we did an assessment, and there's an interesting sort of report available about all that's happening up there now, they consider they're in an emergency situation right now up there. And the Arctic affects us, and this is kind of a fun thing. I don't know if any of you read The Onion, but this figure is from The Onion. This was their view of President Bush's climate control program, was put an air conditioner in Canada. But it was sort of a jokey notion, but I use it because the Arctic is really the air conditioner for our country, for our weather. The weather we have is, we have a very unusual continent. We're the only one that doesn't have an east-west mountain range separating the Arctic from the low latitudes. And so cold air comes out of the Arctic and warm air comes up from here, and they collide, and we get these big convective storms, tornadoes and all the rain and everything else. As you have less cold air coming out of the Arctic and you have more moist air, it's going to change location and shift, and it's going to cause storms. And so you hear about all the problems in the northern Great Plains. If you have 2 inches of rain in Alabama and Mississippi, big deal. The geography's sort of used to it. If you have 2 inches of precipitation up here, either as snow accumulated and everything, they're not used to it, and they don't have the river channels for it or anything else, and you get more flooding. So the Arctic is really important. So you might try and do something to save the Arctic. Stu Ostro is interesting if you want to look at changes in weather and things about this. You've all probably been here in Washington longer than I am. What I remember about Washington from the mid sort of 20th century is the weather is, in the summer, is you get these nice moist hot days, and then a thunderstorm comes by and it clears it all up, and for a day you have cool things, and then the moist air comes back, and then a few days later you have a thunderstorm, and it sort of cycles that way. Well, we haven't had any lack of warm, moist air. A few years ago we had, I think, a couple of months where we didn't have a thunderstorm, I think all through July and August. The lack was not having a trigger. It was not having the cool fronts coming out of Canada down and triggering those thunderstorms. I mean, Atlanta doesn't have a shortage when they were having the drought. They didn't have a shortage of moist air. Okay, so they had a shortage of the triggering mechanism in the cold fronts. And so you get these droughts and everything, and this cold air is less. I mean, the other thing I sort of was asking Bob Ryan about the other night was it's taking longer for the fronts to get here. The weathermen keep saying, it's coming, it's coming, it's coming, and it doesn't come. Well, that's in part because for the front to get here, this cold air has to build up on the northwest side of the Appalachians and then flow over it and come under our air and trigger the storms. Well, if there's less cold air coming out of here, in terms of the mountain stuff, it takes longer to get over the Appalachians. And so we're getting these different kinds of things. So it's affecting our weather. All right, so there are a bunch of possibilities. There'd be a lot of benefits. It would sustain sea ice and the species. It would help reduce erosion. It actually turns out it would keep a lot of precipitation. It would allow more snow and the mountain glaciers and stuff to build up. It would sort of keep the permafrost around instead of melting, so it would be really nice to have. We've done some calculations where you just sort of take away solar radiation up there, and then you run that kind of case, and it turns out, indeed, here's the 2 times CO2 case, if you can cool the Arctic back to about the normal kind of conditions. And it has some benefit in mid-latitude. So if we could do something just in the Arctic, which wouldn't have adverse effects down here, that would be beneficial. And as I was saying, I mean, it takes away the heat. It doesn't take away the precipitation, the increase in precipitation. That's because with 2 times CO2, the moisture that evaporates and precipitates up there is from the warmer latitudes. And so we haven't put anything to slow that down. So it would build up ice and glaciers and stuff. Second one is try and reduce intensifications of tropical cyclones. There's a patent application in by Bill Gates and a few others in that group up there about where to do it, which is to mix the waters. They have a wave pump mixing kind of thing that would try and reduce the temperature of the water in front of storms. I don't think it can do it fast enough. I think it'd be too hard. But you could imagine brightening clouds over the Gulf of Mexico to try and do that. Let's see. This just sort of says the same thing, and I'll skip that. It turns out we also know from out in California, the rain's coming up there, that if you change the gradient in ocean temperatures just by a little bit, you can direct the storm tracks a little bit. And in Australia, the droughts they've been having until they had floods from up in here, is because the storm track has been shifting south of Australia. And if that happens, they lose a lot of their agricultural and other areas here. So the question is, could you go out over the Indian Ocean and affect temperature gradients in a way that would sort of push the storm just at least some years back on here? Could you do that for North America? Because the Southwest North America, they talk about a drought. They're being optimistic calling it a drought. I mean, the Sahara isn't having a drought. You know, this is a shift in climate that's occurring. So can you do something for some of those areas? Can you offset the SO2, the sulfate cooling? I've sort of talked about that out over the ocean, putting more SO2 out. That might be workable. It'd be interesting to look at. Can you do something to try and cool the fjords, the water that's melting? That these glaciers are melting because warm water is sort of coming in. So can you go out in the ocean areas or sea areas to the west of Greenland, for example, and try and do this? And this is really important because if you look at Greenland, I don't know if you've seen this map or not, but until 6 or 7 years ago, everybody thought Greenland was not a vulnerable glacier. Ice sheet. We don't have to worry about it. That's because it's sitting up on mountains. And if air has to get all the energy to the ice to melt it, then it'll take a long time as opposed to the West Antarctic, which is resting on the seabed, and there the ocean can get at it. Well, so some scientists figured out how to go and figure out where's the bottom of the land underneath Greenland. Okay, and it turns out that if you look at, so this is like the surface of Greenland, all this blue area in the center is below sea level. Okay, so it's like an atoll. It's a big atoll instead of an island. And that wouldn't be so bad, except that's connected to the ocean area in a few places here. And this is the glacier that everybody's been talking has been moving so fast. So warm water comes in under here, helps lift the glacier and carries heat to it and melts it. Now, if this much of Greenland is vulnerable, the question becomes how much sea level rise am I going to get? The big controversy in the IPCC report this last time was they said, oh, sea level rise is going to only go up 1.5 feet or something over the 21st century. What they didn't say quite clearly enough for the rest of us was they left out the term of ice moving. Okay, they did that because in the 2001 assessment, when they didn't know that, they had a big uncertainty range. Some U.S. science, the IPCC was coming out, and I was, as they said, in charge of the review process. Some U.S. scientists wrote us and said, the U.S. has to reject that chapter because it's underestimating what could happen. And we worked on some negotiations with the authors so we could get around, and they had a big range about how it could happen, so it went up to 3 feet and stuff like that. But in this one, they decided, well, we don't know that term, so we're just going to say the terms we know, and they left out the big term. That big term over several centuries, people are estimating you might get 1 meter from that, 3 feet per century out of that. That could raise sea level 20 feet. That's how much ice is up there if it happens fast. That's huge. And if you start it, how do you stop it? So where are we now? Well, we'd like to go to 1.5 degrees. Business as usual is saying by the end of the century we're up at 4 or 5 degrees. These are Fahrenheit, so a little different numbers. Or, I'm sorry, well, these Celsius here, 4 and 5 here, Fahrenheit over there. The emissions pledges, if everybody lives up to it, would get us down to maybe 4 degrees. We're still way above this. So what do we do? Well, there's no such thing as a free lunch, Emissions are going to cost money and effort. Got to switch away from CO2. Impacts are going to be significant, so we'll have to adapt. We'd love to get a carbon dioxide removal if we can, but it's pretty expensive to do. And there's solar radiation management. So these are sort of an options, and you need some combination of these options to try and figure out how to do that. It's also complicated a little bit because there are a couple of international conventions on this. One is the one you've heard about a lot, UN Framework Convention on Climate Change, which the U.S. agreed to in 1992, but is this effort to try and get control of the climate, not cause dangerous anthropogenic interference. But with these advertent, these intentional ones, there is something called the UN Convention on the Prohibition of Military or any other hostile use of environmental modification techniques that the U.S. also signed. This came out of Vietnam. It was basically aimed mainly at the weather because the U.S. was in there modifying the weather. It says that's not a fair thing to do. But it does cover the climate as well. And so there's some questions about if this applies. And there's some other ones that apply to dumping stuff in the ocean and everything. So there are a whole bunch of international conventions. So we're basically left with a choice. What are we going to do about all this? It's a really serious quandary. Do we continue with global warming and emissions and ever-increasing risk, or do we try and do something about it? And does that include climate engineering of various kinds? So it's up to us to decide, but note that it also affects not only the environmental creatures, but also future generations. We're putting an obligation on these things on future generations. So it's quite a challenge. There is the back of that PDF file if you want to look some places to go look at some of this in the literature, and there'll be some other places you can find. But that's all. Thank you. First, there are efforts to try and capture the CO2 out of power plants. So if I can chemically capture it there and then dispose of it somewhere, it might be underground somewhere, it might be under the ocean somewhere, And there are a number of others who are instead taking that CO2, putting it through a greenhouse, growing a lot of algae and making biofuels, which means you're sort of getting 2 times the energy out of that carbon atom that you release, and so that makes it more efficient. And the CO2, as I sort of indicated in the power plant stream, is maybe 10 or 20% of the air, so there's plenty available, and it sort of works productively pretty well. The other question is, can you take it out of the atmosphere? Can you just scrub it out of the atmosphere? And there's even been some prizes set for people to try and figure out how to do that. So there are a couple of groups trying to figure out how to do that. But the CO2 is very dilute at that point, and so it's really hard to do. You can let plants do it and then burn it as biofuels in a power plant and capture that CO2 and bury it, but you have to then have this technology to do it in a power plant. There are people who want to try and scrub it. They have a sort of a catalyst that goes in where the CO2 adheres as the air blows by, and then they take it to somewhere and you heat the catalyst a little bit or something and give off the CO2, and then you try and bury it. But nobody's figured out how to make that cost effective unless you get up at several $100s per ton of CO2. So that just says get a tax. And at that point, you should be doing all these other things, efficiency and everything else. You could. It turns out following the volcanic eruptions, when we get this imitation of what would happen in the stratosphere, the biosphere actually takes up more carbon. And it does that because we think the light gets scattered, and so the light comes in from more different angles in a forest canopy and gets to lower in the canopy, and you get some different plants growing and more growth lower down. Now that'll change the ecosystem, and nobody knows quite how far that would go, but you have some effects. But there are a huge number of potential environmental effects if you start having more diffuse radiation. I mean, some animal, bees and other things, I think, see in different parts of the spectrum and other kinds of things. So there are problems like that. There are ideas for saying, well, why use sulfate in the stratosphere? Why not figure out some small particles that instead of scattering forward 10 times as much radiation as they reflect, just reflect radiation, okay? In fact, Edward Teller had a very interesting idea for how to do that. I mean, if you have a corner and you have a handball or something and you throw it into a corner like that, it will come out in exactly the same direction it went in as it bounces off the walls. So if you could make little particles that are all made of corner reflectors pasted together, then the sunlight that comes in on them would reflect right back out, and you could make them of a size so you don't have too much scattering. Now, that's not easy, and you have to figure out how to keep them up there and a whole bunch of issues, but there was even a patent issued in the mid-1980s by a person from an aerospace company who had a particular metallic compound that he thought would reflect more efficient as a reflector. So type of particle is something to look at. Sulfur is cheap, and so these particles might be expensive, and so that becomes an issue. I once actually did a poem about it with Scientific Answer, which in the end talked about some balloons. I mean, President Bush Sr. had his, 1,000 points of light or something. I had my trillion points of light, which were balloons that would reflect. And everybody said, yeah, but then the balloon will pop and it'll come down and rain on you or something like that. So there are a bunch of ideas. They haven't been looked at in any systematic way. The countries just haven't thought that it's worth doing yet. So. Well, you're exactly right to be thinking about that. We're all concerned about that, and the answer is no. There's nobody working on this. The Royal Society had a report almost 2 years ago, and there are a few little efforts in Europe that are starting up as projects to see some of this, and there are a few projects in the U.S. looking at using climate models and other things to try and see how much you would put in or patterns or something like that. But there's no research program on it at all. It isn't an option right now. It's not an option because Well, I think it goes back to actually to the 1950s. There were ideas and notions coming through the 50s that society and engineering could do anything. So we were going to have nuclear power, and it was going to be too cheap to meter and everything. There were also at the time suggestions about changing the Earth's climate, about melting the Arctic sea ice in order to go up there and get the resources out and stuff like that. For quite a number of reasons, nothing came of that. And thank goodness, now we want to keep it cool or something. But that sort of hubris about changing it created a reaction. And so although there have been sort of a very low level of people speculating about the issue, there's been no research, and virtually none in the research community, about this. It came up in this 1992 National Academy report. They listed a set of the possibilities. Nothing came of it then. It arose a few years ago when Paul Crutzen, who's a Nobel laureate for the ozone problem, and had also been elected to the legislature for a while in, I think it was in Germany, basically said the negotiations are going nowhere and the planet is getting warmer and warmer. We better start thinking about this. And so it's come up and gotten raised as a rather prominent issue. President Bush Jr., or second one, when he came in 2001 and put forth his energy program, his proposed energy program, had 8 or 9 points on it. One of those to look at was geoengineering. There was a workshop held by DOE. I was one of the helped them organize and thinking about it. They never published the report. They did that nobody knows quite why. But there were several plausible reasons. One, if you admit, if you're going to do this, you have to admit there's a problem, and they didn't seem to want to admit there was a problem. But second is, if that becomes your strategy, does that take attention away from mitigation and reducing emissions, which you have to do first, which was one of the points made earlier and which I tried to say. I mean, you can't geoengineer your way out of the total big problem. You may be able to do it out of this other one. Now, will there be side consequences? Yeah, there's no such thing as a free lunch. Can we keep them limited so that they're less than the consequences of not doing it? It's not a question of do I do geoengineering or not. It's a question of do I have global warming with geoengineering or without geoengineering? That's really the question one has to ask. And we're so far along, we're going to have this or something. And the question is, do I try and moderate it? And is there a way to moderate it so that the consequences are less than for others? Now, there's going to be winners and losers, and so that's going to make international negotiations very difficult, if possible at all. And so some people think, oh, this is just hopeless kind of things. But even if it is, it gives everybody a sense of how big the problem is and the predicament we're in. So it might even spur mitigation because you might say, well, I'd like to avoid that so I don't pass responsibility for solar radiation management on to future generations, for a century, that they have to do it. Because, there are very few organizational entities in society that are multi-century long. There's sort of churches and universities, and is that how you're going to sort of work your way through and trust that it will keep getting done? And how do you think about the moral aspects or ethical aspects of that? Very difficult questions. Yeah, that's been one of the things that's been covered a lot in the literature as a possible problem. I'm sort of, I don't think that's quite the major issue. I don't think you could do it undetected, although there are people who have actually tried to write novels about doing something like that undetected. Manufacturing these little reflective particles and putting it up there. I think we know what would happen. It's also such a diffuse kind of benefit to people, it's hard to see how you would do some of these things in a global sense, how you would do something. First of all, testing isn't going to do much. I mean, most of the testing that you're going to do is going to be pretty limited. I know there's some people say the only way to test it is to really do it. But I think there's a lot of things you can measure and figure out if it would work Well, otherwise, we know from volcanoes it would work. So there's some things we can test about how it goes. So I'm not so worried about the testing phase, although we had a major conference in Asilomar, California, a year ago that sort of got people together about what are the ethics of, what are the ethical considerations for the research community about moving ahead with research in this area. And we came out and identified a number of principles, and we did ask for some body to be formed, some entity to be formed that would look at these kinds of things, because it's hard to imagine how scientists would get permission to go ahead and do these things or something like that. And so you'd like that to happen. And there are some governance conferences taking place about how might it happen. I mean, is it the UN that does it? If you do some of these regional things, I mean, I've been sort of favoring going to some of these regional things first. Don't start out at the globe. Why jump there? But if you could, if blowing seawater up would help brighten clouds over the Gulf of Mexico and cool that temperature down a degree or two and keep it sort of where it is or a little lower or something like that, so that hurricanes didn't intensify so much when they came across that, that's going to be an impact that it mainly affects us and the countries of the Caribbean region, who might favor that as well, to try and limit the warming of waters where hurricanes intensify. So you might be, if Australia were to do something about a storm track down in the Indian Ocean to try and affect temperature gradient there, that wouldn't have much effect anywhere else. The Arctic one does have some effects elsewhere, but if you do it in the Antarctic, you can actually sort of try and balance them over the Southern Ocean. So there may be some ways to get around it, and those are getting looked at. But you're right. I mean, there are these issues about doing it. I don't see it sort of as a military thing, although there are military implications of the Arctic opening up, and one of the issues is trying to refreeze the Arctic or something like that. But I don't quite see it as the military kind of thing. I think the other issues are much more difficult than those ones. But a personal view, Well, on the first one, that's an interesting question. One of the things I, as a scientist, got asked to do was advise the Catholic bishops when they were putting together their statement, almost 10 years ago now, I guess, 8 years ago, about that, because they sort of said, aren't we going to get, if we say something about climate change, aren't people going to come about population and birth control and other things? It really depends on what the choices are people make. If we only had the 1 billion people we had in the developed world, and we keep doing what we're going to do, we will continue to have this kind of climate change. So we alone, with nobody else in the world, could do it. One of my papers a few years ago focused on this notion of trying to make a deal to break this deadlock between developed and developing countries, to get the developing countries to focus on short-lived initially and us to do the long-lived. And it was to basically say to both sides, look, President Bush at the time, even if there were nobody in the developing world, if the developed world continues on its trajectory, we are going to pass this dangerous level sometime in the mid to late part of this century. We have to change our ways. Developing world, even if the developed nations were not putting out anything, if our emissions instantly went to zero and they continue on their trajectory, we will also pass that threshold. And the differences are only by a decade or two. We both have to act on this, so we really both need to be serious. But it depends a lot on what the choices we are, what choices we make about what kind of energy you choose, where you get your energy from and how much you're willing to pay. And if you can do renewable and other kinds of energies that have much more modest, sort of more local impacts, then you can do better. If you try and have everybody get it from fossil fuels, you'll be in trouble, and that applies to any subset of the world population. Are there thresholds? Yes. We don't know where they are exactly, but it's pretty clear there must be some. One is there's a lot of carbon that would probably come out as methane if you melt the permafrost. Well, we have a freezing point. If you start getting the temperature up, we know we melt the permafrost and methane comes out. It's starting to bubble out in some places around the world already. Same with the ice sheets. You have ice sheet up on Greenland. If you get it so that there isn't snow up on Greenland, and they've had places where they've had rain in some months up on the top of Greenland, you won't build up the snow and it will start flowing out, and it's got 20 feet of sea level equivalent in it, and from the looks of it, it has the potential through these fjords to flow pretty fast. And once it gets started, then the level of the ice sheet goes down, and as you get lower in the atmosphere, things get warmer. So it's warmer, and you keep going. So yeah, we'd love to avoid those kind of thresholds, and there are certainly others. But those are a couple of examples that we'd very much like to avoid. And that sort of was why they chose 2 degrees as a sort of level of danger. Now, there's a conference you may be reading about in the literature called the Anthropocene, which is what that Nobelist Paul Crutzen developed as a term, that we're switched from sort of the natural world controlling for the last 10,000 years, since the ice glacial period, to humans taking control of the system. And they're calling it Anthropocene, and they've sort of proposed some limits to try and make sure you don't do much. And the proposed limit on CO2 that they've been using is 350 parts per million. So that's below where we are. We're already past that, and we're already past it on the nitrogen cycle and some other things. So yeah, there are some thresholds. We're worried about it, and that's why scientists are speaking out as much as they are. There are a whole bunch of notions of things going on that may be changing the climate and everything. That the Air Force is going around putting out a sort of mist up there and doing things. No, I don't think there's any of those kinds of things going on. I mean, changing the global climate is a huge effort. And stuff. Changing the weather is a very large effort. There are, a few little things going on. I mean, the apparently Department of Homeland Security is trying to see if there are ways to try and limit the intensification of hurricanes. At the moment, it's mainly a theoretical effort. It was attempted in the 1960s out over the Atlantic to try and do that. They ran into a number of problems. One, you had to be so far from land to do the experiment that it was hard to measure things. Second, each storm was different and you didn't have any good control, so how do you figure out if you've made a difference or not? We've gotten around that problem because now we're getting better and better computer models, and you can try and experiment a little bit in that way. But the main problem is if I change something out there and the storm comes in and hits somebody and does something, you're going to get blamed for it. And so there's a huge legal liability issue and everything. I gave a talk on geoengineering at the Vatican Pontifical Academy of Sciences a couple of years ago for various reasons. And one of the things in summarizing I said is one, sort of irreverently, if I admit, but was, if we go to a geoengineered world, it's going to be as if there are no acts of God, in an insurance sense. Because everybody's going to be saying, you say you can control it, then everything that happens you're responsible for. The cardinal smirked a little bit, but